the lecture. The good thing is that there's nothing later, so we can stay 3 hours, no? Slightly. No, I will try to keep the time. So, in fact, this lecture is divided in 2 parts. So there is part 1 and part 2. Okay. First, I will discuss a common framework for depining and yielding, things that I've discussed in the first and the second lecture. Okay. This is more a conceptual or theoretical idea of way of thinking that, in principle, is a talk that was intended for specialists, but I adapted a little bit. But for you to get an idea, how do we try to think on this field and build analogies between one transition and the other? And if you get lost, raise your hand. I replay. And the second part will still be using depining and yielding models. So I don't go out of the field, but it's more about an application on a different field, which is geophysics. Okay? So let's start. And as always, before start, I want to acknowledge my collaborators in the things that I'm going to tell you today. They are, I think, 2 of the greatest scientists in this field, and they are both in my corridor in Bariloche. So we are colleagues at Centro Atomico Bariloche in the condensed matter group, and so I'm very lucky to have them there and discuss every day with Eduardo Hagel and Alejandro Colton. So, as I said, we'll try to unify, unify descriptions, unify everything. The guy is not happy with the amount of universality of his previous lectures, wants to also be everything the same thing, okay? So unify first the description. So I will tell you why we can represent the yielding models or the lasoplastic models that I told you yesterday as a more depining-like model, and then unify the problem. So interpret the problem of yielding in finite dimensions as a limit of mean field of the depining problem. So more or less this is the idea. This you have seen already, so we will just review it. This is the depining transition, remember, of an elastic manifold moving in a disordered media, like a magnetic domain wall. We represented it in models that thinks of part of balls or springs, or this equation of motion, the so-called Quench-Edward-Wilkinson. The thing is, this is a manifold moving in a disordered system represented by this disordered landscape for each portion of the line. And it has the transition that below certain force there is nothing, also velocity is 0. Eventually the interface moves a little bit but gets stuck again. And you have to overcome a critical force in order to have a finite velocity in a steady state. If you have finite temperature, this transition is rounded, and we'll talk about this today. What I want to tell you here is that, well, typically we have these short-range interactions for the elasticity, just springs between the neighbors. But in the case of long-range elasticity, which is also in the case of, for example, the partial wetting line or the crack propagation, we have to replace this by some force that has a long range. And we typically write it like 1 over the distance to d plus alpha, and this alpha, you change it, and you go through different levels of long range. When alpha is equal or smaller than 0, you say you are in the fully connected case already, okay? So you are, well, it's so long range that is like a fully connected network, okay? When things decay as 1 over r to the d or more slowly. And there are many exactly known results, okay? That I will use some of them. On the other hand, we had the yielding transition of amorphous solids under imposed, for example, shear stress or deformation. And remember that we had these stress strain curves, eventually reach a plateau. And if you plot the value of the steady state stress as a function of the velocity of the deformation, the strain rate, we have this kind of curves that flipping the axis was the same as saying, okay, strain rate is my order parameter, my control parameter is the stress, and here I have, again, a critical transition, a phase transition. Below sigma c, there is no movement. Above, there is a finite velocity of the formation of the material, and the only difference with the pinning is that the beta exponent in this case is bigger than 1, so we have the other curvature for this line. And remember that one ingredient of yielding was that when some plastic event happens in a given place, it affects the rest of the system in a long-range way through this SLB propagator that comes from elasticity, mechanics elasticity, and that has this 1 over R to the D dependence and a cosine for theta in the angle. Okay, so in fact, I show you more in detail here, again, what were the elastoplastic models that we used, equation of motion for each value of the stress on the lattice, on each block of the lattice, a global loading, a term that will make the local stress go down exponentially when the site I gets fluidized, and then this site I is always receiving kicks or mechanical noise for the plastic activity in the rest of the system through the SLB propagator, okay? We complemented this with local rules to say when one site needs to fluidize itself and when it recovers full elasticity that are basically n going from 0 to 1 and then going back from 1 to 0, okay? So if you think a moment about this, maybe I haven't mentioned it yesterday, this is a very phenomenological model, like built in the kitchen. It's not thinking about properties of dynamics that we decide in general. So for example, this state, when a site fluidizes, and then it will be in that state of fluidization during a certain time or for a given, yes, during a certain time or stochastically with a certain rate, we are keeping a memory there locally. So if you are at time t, you go to time t plus 1 in a discrete version, you are keeping memories of what has happened in probably time t minus 7 or whatsoever. And this makes this kind of modeling non-Markovian, okay? So we have local memories. And in fact, we cannot derive this from Hamiltonian, okay? This is a nice dynamics because you can reproduce experimental curves, etc., tuning the parameters, but for statistical physics, it's a bit annoying. So the idea now is to put both frameworks of yielding and the pinning together in, of course, the most treatable one, which is the one of the pinning, where we know we can derive things from Hamiltonians. So people have actually showed this exactly, but the basic idea is that if you start from an elastic energy for your system, you have to think on 3 types of strain. So one bulk strain that changes volume, and 2 shear independent one. Okay, with these 3 type of strains, you represent all kind of deformations you can have in your material. So, and you see, I mean, it's like being in 3 little parabolas in different directions of the strain, if you want. If allowing for plasticity basically is to allow your local block, to undergo plastic deformation, which is escaping from one parabola, okay? And we can do this. I want to simplify at the end and have a scalar description, not all components of the strain. And you can say, okay, let's allow E3, which is one of the shear components, to actually, instead of having one parabola, having many little parabolas, one after the other, and you can jump from one to the other. And you can do this, and of course, there are constraints, because if you deform it like that, other things, I mean, you cannot deform every block in every direction, because you have a material that has to stay mechanically together. And then there are some constraints that are Saint-Venant constraints, and which make these things emerge. Remember that when I told you the finite element methods model yesterday, it was the same case. You don't put by hand the Eshelby, but it comes out from the dynamics of the thing. And here it comes through this kind of movement plus the constraints. It can be quadrupolar in this way, or maybe more oriented towards one axis or another, depending on many details, but it always has positive and negative kicks. So assuming an overdamped dynamics for, and that E1 and E2 relax much faster than E3, then we can keep an equation only for E3. And we can think that now E3 is the strain associated to the stress of the elastoplastic model that we were moving. So basically, let me probably do a drawing because it's important. So remember that we have these kind of things for the local stresses of the elastoplastic model, okay? So it loads, then decrease the stress, then it loads again, decrease the stress. So you can think, again, as this being now the strain associated with this stress, and that it increases, goes up, the stress goes up, and when it overcomes the barrier, goes down, okay? And so basically this is the same kind of equation of motion that we have for the position of the manifold in the case of the pinning, but now for the strains of a manifold that represents the amorphous system. And I'm just changing here the elastic interaction, short range or long range in the pinning, by the Eshelby interaction, which is we know the characteristic of the amorphous solids. And then still we have a pinning force coming from a disordered potential, and the drive will be now the stress, okay? So we can build this analogy in a modeling analogy. And then this force comes from a potential that can be different. I mean, you can choose many things. If you choose something like this, which are flat parts and traps, okay? It's more like the elastoplastic case where you are fluidizing when you can move freely, and when you become elastic again, you are in the trap, okay? So the case is 0 and 1 that we have here. Basically could be represented by this. But then instead, you can describe a little better this trap and say, well, there are little parabolas, and you can shrink the flat parts, and eventually you see that the physics is the same if you use just concatenated parabolas, and nothing changes in the critical properties of the system. So, and this is more typically what we use in the pinning. We will think then the yielding model, the amorphous solid, as an elastic manifold moving in disorder. And now we have the property that we can derive this dynamics from a Hamiltonian, okay? This is what I said before, but now we don't have the states Ni because it's just described by E. Okay. So we build the Hamiltonian model for yielding. And again, it's the same equation as before. This is the force coming from the disordered potential, the Eshelby interaction, the global driving, applied stress, and we could add a Langevin term for temperature now, okay? And Okay, then we will use two kinds of disorder potentials, the ones that I call CASP, which are concatenation of parabolas like this, which has discontinuous derivative in the transition from one well to the other, and others that are more sinusoidal-like, which are called smooth, okay? So you can always build these things by combining signs with random phases, so yes?
The image that we can have is the one that you have this front, and then you are pulling with the force.
Yeah.
And you have this elastic energy given by the propagator.
Yes.
Plus an external.
Yeah, now you don't think in the shear like this. So if now this is your system, the shear is like that. I mean, you are moving the interface in disorder just like this, but now like a 2D manifold. And the previous global shear that was stressing locally the blocks like this is now represented by a force pulling this manifold.
Yeah, but yes. But my difficulty now is that what is the difference between this external force and the one that was pulling, you know, the front before? They look like pretty much the same effect for me. You know, those two.
Sure. I mean, these are the same. So what has changed here is that when I write the elastoplastic models, this is variable, and the controlled external forcing is the gamma dot. Mm-hmm. Okay. Now I flip things around again, and I put the change in time of the strain, so the strain rate again, gamma dot, as a function of a control stress. I mean, in both problems you could do either control stress or control strain. When we write it in the way of the pinning equations, it's like this. I mean, the stress plays the role of the force. The strain rate plays the role of velocity.
The strain field is the elastic manifold moving?
The strain, yeah, indeed.
The strain field.
The strain field. This is the strain field. So it's like strain in each block of your system. Okay? And when you apply a global stress to that, it's like you are trying to pulling this strain FR. So, okay? What I'm saying that it just moved forward is because, I mean, when you jump with the strain field to another parabola, in particular, we can keep the full potential quenched, but in the yielding model, it doesn't matter when one side overcome a barrier fluidized plastically, the configuration changes completely. Then it's not that if you go back, you recover the previous configuration. You will have a barrier there to come back, but then the well can be deeper or shallower. It doesn't matter. So that's why there was, it's there. This little internal degree of freedom there is just to say, each time I jump, I change the disorder, okay? It's dynamical. Okay, but I mean, there is this, which is done here, also by Alberto Rosa and others. You start from a tensorial description, and you show that, of course, in a given approximation, that E1 and E2 are much lower than E3, et cetera, et cetera. You recover this equation of motion for the yielding problem. Okay, so the first thing I will show are flow curves, and that we have seen already yesterday, but now with the Hamiltonian model. And again, when you have a CASP potential, the flow curves which are gamma dot as a function of the stress, when you subtract the critical stress, they are a power law and have one exponent when they are CASP, another exponent when they are smooth potentials. Okay. And okay, this is another example of the same thing. Just to say, I mean, if you change parameters of your model, this is one simulation with one parameter. You see the critical sigmas are like here, and here are completely different. It doesn't matter which is the critical stress, which is not universal, but then eventually for the exponent, you get the same thing, okay? So there are two relevant values for beta in the yielding case. And this I will fast because it's just repetition of what I told you yesterday. This thing we have already obtained with elastoplastic models, the classical elastoplastic models, by proposing a different rate for the local fluidizations. Remember, all classical elastoplastic models have a fixed probability of yielding once you have arrived here. It doesn't matter how much you are stressed. And then we propose the progressive rate to say, well, if you are more and more stressed, then the probability of yielding should be bigger. And there is a mapping between uniform rate and progressive rate with CASP and smooth potentials, okay? So I already said this yesterday, but when you have a CASP potential, typical time from going from one well to the next one is a constant, is a characteristic time, while when you have smooth potential, you have this saddle where you can live for a long time, and then, in fact, the time depends on how much you are tilting the potential as 1 over the square root of this delta sigma. But if you do in elastoplastic model the flow curves, again, you have 3/2 for the uniform yielding rule, and 2 for the progressive, which is the same as saying as 1/2 for CASP, 2 for smooth potentials, okay? And again, here I'll use an exactly known property of the pinning in the fully connected mean field. As I said, when alpha is 0 or smaller, we are in this case. So these are the values of beta for the pinning problem. People have worked in the pinning problem for many years, and so there are values of beta known along all these values of alpha, different range of interactions. And we know that when alpha is bigger than 0, beta always renormalize to the exponent of the CASP potential. It doesn't matter if you use this kind of potentials, okay? What you get in simulations or in theoretical calculations where you do renormalization group, etc., is that you get the exponent of the CASP. So it's universal up to alpha equals 0. In the fully connected mean field problem, both values of beta survive, and you have 2 universality classes, or at least 2 values of beta, okay? And okay, now we have yielding, and we clearly have 2 values. And remember, how is the Eshelby propagator? Is R to the T, so it's case of alpha equals 0. So basically, we are in the case of alpha equals 0, and we have 2 values of beta. And so this is compatible with a fully connected mean field pinning, okay? Exponents are different because propagators are different. This one has positive and negative kicks, etc. This is purely positive. But anyhow, a difference of 0.5 in between 2 exponents is seen in both cases, okay?
But is that something that you expected before, that you could change the exponents, but this difference should be the same?
No.
Okay, it's just an observation.
No, it's an observation. In fact, I don't have an explanation. So Eduardo's today show also 2 cases where the difference is 0.5. But I don't know if it has something to do. In any case, here, this is kept there. I think that it shouldn't be a coincidence. There should be a reason for that, but I don't know what it is.
Oh, actually, but if you just come back, what Eshelby is the one that has been shown that works for elastic systems, right?
Yes, that one.
So that
yeah. Now they are using it for glasses over cool liquids.
Okay, but then does it? What would mean to change alpha? You are thinking about different type of elastic medium?
No, sorry. Alpha. So yeah, in the pinning problem of an elastic interface, you know that, for example, if you describe a magnetic domain wall, short range is enough. Alpha equal 2 is enough. If you are going to describe a crack propagation, you have to go somewhere here in the long range. Okay.
Okay. I see.
But okay. So
Okay,
this is
so there are different mediums
for
which
the elastic,
those-
for the elastic, amorphous elastic solids, etc. We only use this. Now,
Yeah.
okay, there are people talking about screening of the interactions, meaning that in principle we have this, but because of the plastic activity that's going on, it does not go 1 over R to the D all the time, and then there are some screenings like you are cutting the range of this interaction. So in fact, there are people in the field doing shorter range elasticity as well in amorphous solids. But okay.
It just bothers me that if you, let's say, if you take alpha equals to 0.1, you just go out of this, this non-linearity there.
Tac.
Yeah, then, I mean,
No, I mean, you see, there is a globe here, it's
Okay,
called beta
okay,
F,
okay.
because go and measure there, you will obtain whatever in between.
okay, then it's
Yeah, it's
bother
difficult,
less.
it's difficult.
Okay.
It's numerically difficult to actually observe this, but they know exactly, okay? So the first observation is that the flow curve exponent beta of yielding in 2D depends on the type of disorder or the yielding rule, just as in fully connected depinning. So this is an observation. Now let's go to thermal rounding. Just let me just recall you that in analogy, so this was proposed by Fisher many years ago, in analogy with the ferromagnetic phase transitions, when you put an external field, you round the transition of magnetization with temperature because you break the symmetry and you allow to have a finite magnetization at high temperatures where you shouldn't have it anymore. Well, here is the same. Below FC, there should be no finite velocity, but if you put a little temperature, you allow the system to unpin from the disorder and have some finite temperature. In fact, at the critical force, the velocity goes as T to the phi, and this is a new critical exponent. And you can propose this scaling law for velocity as a function of the force and the temperature. Following the analogy that I just mentioned, we want to have this at the critical force, but also in the limit when T goes to 0, we have to recover B going as F to the minus FC to the beta. So basically, this function here should be its argument to a power beta, okay? In order to recover here F to the minus V to the beta. And then whatever is left for the temperature should cancel, meaning that phi should be beta over alpha, okay? So we have, okay, this alpha is not explicitly mentioned here, but is the exponent that controls the barriers, okay? How the barriers are suppressed by temperature, okay? It can be different things, but once you have one alpha and you know beta, then phi will be just beta over alpha. In yielding, we will have a very similar thing, just that since it has already this curvature, it's difficult to see a rounding, but I mean, you could imagine it there. It's easier if you put this scaling log, and this is a curve of T equals 0, and a curve of T bigger than 0 will be something like this. At a given strain rate will be like a stress depletion, okay, due to the temperature. So we propose the same scaling law, okay, and now it's sigma instead of force, and say here, alpha describes how energy barriers vanish, okay, and we know that for Caspi potentials, alpha is 2, and for small potentials, alpha is 3/2. So believe me in this, so I can continue. According to the type of potential, this exponent is different. And then we will propose this and we'll try to test it. So first we test it in the Hamiltonian model, where we added the temperature with the Langevin term. So this is a proposal scaling. These are curves for different temperatures, okay? This is sigma C, when temperature is 0, and then different temperatures, as I showed you pictorially in the previous slide, have different curves like that. And when you propose this scaling law, curves collapse very nicely in only one master curve. Here, we are in the Caspi potential, alpha is 2, beta is 3/2, then phi is 3/4, and they are the numerical values we have used there, okay? The same for the smooth potential, so I can jump. So the thermal rounding scaling works very nicely around sigma equals sigma c in both cases. We have done this also with the elastoplastic models in this work. And I mentioned already how do you put temperature in the elastoplastic model is allowing, okay, is now an arrhenius probability for jumping the barrier. Say when before arriving, even before arriving to the yield stress, you can activate because of temperature, okay? So now you yield when you arrive to the yield stress, and also when you, with a given probability, when you are below. It's pictorially there. Okay. May go faster because it's just a repetition, but in the elastoplastic model, we obtain the same kind of things with the same exponents. Okay, there is a little detail, it's just that now we don't have the potential, so alpha is not necessarily fixed by the kind of potential you use. It's another parameter that you put here. So if you, for example, use here alpha 3/2, but you are doing a yielding rule that should correspond to beta 3/2. The only way this will collapse is when you put phi equal to beta over alpha, so 1. Otherwise, if you use another, try to use another value for the phi, it does not collapse. So it will collapse when you use the correct exponent coming from alpha and beta. Okay, so this is the summary of this thermal rounding part. The thermal rounding scaling works with no corrections for yielding, so it's really like if you were in mean field. And we have two relevant families linked to the exponent, the Caspi and the smooth with alpha equal 2, beta 3/2, and then phi 3/4, and in the smooth 3/2 to 1/4.
Can you elaborate a little bit on the no corrections part? What do you mean?
What I mean is that this is in contrast with what happened with in the pinning short range, which is here. So in the pinning short range, this scaling law was proposed, and you can measure a phi, etc., but there are logarithmic corrections to this, and even this exponent is not robust. It depends on things, etc. And what I mean, no correction is, I mean, basically this, no? You don't.
Are these log corrections due to being close to a critical dimension? Or so,
Yeah, well, I mean, all this is about arguing that, okay? So what I want to tell you, I tell you already one reason, now this is a second observation. The standard Alla-Fischer thermal rounding scaling, which is something in mean field, works just perfectly for yielding in 2D, just as in fully connected pinning. So what I'm saying now is, I will repeat it again, yielding in finite dimensions, 2D, 3D, whatever, finite dimensions, is like a problem in a fully connected system. So because of the long range interactions, it's like effectively in mean field. Okay? So this is a bit of argument. So I have a parenthesis here, but I think I will need to jump it. So when we did this work of the thermal rounding, there was an experimental motivation for the case of metallic glasses where there is a very well-known Johnson and Samuel law, very universal as well, that we can recover from the thermal rounding scaling, but let me just skip it because I'm talking too much, basically. So let's go to the third observation that points in that direction. Now, I'm thinking, okay, this yielding in 2D is like, it's behaving as a fully connected pinning in many ways. Okay, let's mix these two problems in a unique equation of motion that we can tune to be either the 2D yielding or either the mean field pinning. Okay, so we wrote again our equation of motion. Just see that it's now written in the Fourier representation. So this is the same as before. the manifold, but everything sub Q because it's in Fourier, because it's easier to do it there. If I put the HLB propagator there, I have a 2D yielding problem, okay? If I put -1, or probably it should be -1 over n, I don't remember, but a constant there, it will be the fully connected depending problem, okay? So we do a linear combination of these two things with a parameter epsilon, and we vary that when epsilon is equal 1, we will be in the case of mean field depending, and when epsilon is 0, we will be in the case of yielding, okay? And we do simulations varying this parameter, okay? I just shown you here the 3D propagator, just for you to see that the similarity between these two things is that both are order q to the 0. This is a constant, and here you have q squared, q. So the order is the same in numerator and denominator, so both goes as q to the 0. So they have the same range, exactly the same range. In Fourier, you can see it more clearly. And in the 3D propagator, you can also see the same. So we do this combination, and we do simulations for different value of epsilon. And everything that happened for Caspi also happened for smooth, so let me just tell you this. Here I show the flow curves when changing epsilon, as I said, from 0 to 1. And what we see is that the exponent smoothly varies from 1, which is the beta of the mean field depending, to 1.5, which is the beta of of the yielding. So none of the two problems dominates over the other. When you mix them, they just smoothly collaborate to have an effective exponent in the middle, reaching one limit, one problem, and in the other limit, the other problem. Okay? And why is this surprising? I mean, typically, if you combine two different criticalities, let's think about an Ising model with long-range interactions and short-range interactions, okay? Or two different long-range interactions. You can do the simulation and see when you approach the critical point a mixture of things. But when you go to large enough scales, the criticality that will dominate is the one of the longest interactions. And then all the short-range interactions, they don't matter anymore, okay? So typically, this is what happened. In this case, it's like both are the same range, then both matter. And then you have these effective exponents in the middle. It's not that one dominates. And you can see exactly the same thing with the avalanche exponent, okay? That goes from 1.5 in the pinning to something 1.33 in yielding, remember, in 2D. Or for the scaling of this quantity x min that I defined yesterday, the typical distance to trigger the next avalanche. It changes smoothly with one exponent in the fully connected the pinning case and one exponent in the 2D yielding case. Okay? So message here is that both problems are contained in a more general one. Okay? So third observation is that the HLB propagator is order q to the 0, just as fully connected mean field depending. And there is a smooth variation of exponent when switching between one and the other with this. Yeah, tell me. Yeah, okay. Take the chance to.
I mean, so in general, when I see situations that have a smooth variation of the exponent, I expect that you don't have universality in some sense, right? I mean, a universal thing, I would expect to see a crossover between the two exponents rather than the variation.
This is what I was mentioning. Yeah. So what I'm thinking here is that there is a kind of family of problems. If you stick, the tricky part is that we are changing the interactions. So you see a crossover of exponents because we are representing here many problems because I'm changing this. If I stay in one limit, I'm into the yielding. If I stay in the other limit, I'm in in fully connected the pinning, and then there is universality for this problem, no problem. Okay? So there is no issue. Now you mix two problems, and we vary the interaction a long way. So then you see a continuous of exponents. It doesn't mean that each of the limit problems don't have universal exponents. It's just that exponents are changing because we are changing the problem, okay? We are changing the interactions. But then what you mentioned, I just said before, typically when there is a fixed interaction that is the longest range interaction in your system, that one will be the one that dominates the critical exponents, and the others will not matter anymore.
I mean, this is out of equilibrium, so it's a bit of a hypothetical, but if you imagine an RG flow for this problem, for instance, you wouldn't have isolated fixed points for the two problems. You would have, in the best case, a continuum of fixed points, right? Like you do in certain
yeah,
problems.
well, this, in fact, I mean, this is something that we are trying people that do FRG to try. We don't know, but there are a lot of indications that these two problems belong to a more general one, where you have a tuning interaction. And yeah, I mean, you should be able to go and do FRG in this combined problem and see what happens as you change G. Now you can think more generally, anything that preserves this property, that is order Q to the 0. Vary the interactions in this region. Yeah, I mean, I've been talking with some of them like, with the computer like this, and then try to, but okay. They're doing all the stuff. So, proposal is that yielding in finite dimensions should support a mean field or one particle description. And the idea is to plug the effective noise in a one particle model and recover the flow curve. So we don't know how to do FRG, but we can measure this disorder and then do another simulation with the one particle and this disorder. So what we have done for the 6 different elastoplastic models that I presented yesterday is to measure in time, in the steady state, a noise. What means is we want to change this term of the interactions just by a given noise. We want to characterize it. So in the quasi-static limit, we compute this sum as a function not of time, but the number of avalanches. So we are in each point here accumulating all the kicks given by avalanches. Okay, because because we believe that they are the objects that are in fact given the mechanical noise, and in quasi-static limit it's easier to do this. So this is the definition of psi. Okay, and you see already that this is not a random walk. No, you have these levy flights, these big steps, and next. And here you have the cast pure uniform or smooth or progressive for different tree. So it doesn't matter which kind of rule you will have the same kind of statistics.
You are showing us the noise. I thought the noise was an entrant. That's one that you are imposing or you are measuring?
No. This, I'm simulating the equation of motion on the top. Okay?
Yes.
And I'm measuring this.
But how come that you simulate the first one and the second one?
No. The second one, sorry, it's just to show it like this. We want to replace this later on by a problem of one particle just without any interactions or space where I plug a noise there.
Instead of the first?
Instead of the first, but all this data is for the first one.
Oh, I see.
And what I measure is that. Okay? If we assume that this noise, which is not random walk, has a characteristic Hertz exponent and is homogeneous in this sense, so when you rescale x, you have the rescaling factor times this exponent again, so it's a self-similarity of the noise. Then you can do what is called a determinate fluctuation analysis to extract this H, okay? We do statistics, to do this analysis, and we find for all the systems that H has a value around 2/3 for all of them with some distribution. So basically, we can say, well, our noise is characterized by this Hertz exponent, 0.67, and you have to compare it with a random walk with a 0.5 or a noise generated by single HLV events that has h equal 1. So the noise, the kind of noise that will give this Hertz exponent will be noises distributed in this way, as 1 over, so the distribution of delta xi, or the kicks that the noise gives, goes as 1 over 1 plus 1 over h, okay? In fact, this has been previously studied by Mathieu and Nin, but they were saying, well, the only physical possible exponent is h equal 1 because HLB goes as 1 over whatever to the 2, okay? And we are proposing, well, no, there is a noise emerging from avalanches that has a different, that has a different h. And this is the one that will give you effectively the same flow curves that you obtain with the full model, okay? So in order to build this one particle system, we say, okay, now our system is one particle pulled in a disordered potential with the spring here, and we will add the stochastic mechanical noise to the u of t here. So basically, you have this equation of motion. This is the disordered potential. This is the value of the spring. Okay, it's k0 there, and this is the position that you control, and this is the position of the particle. So basically, this is the equation of motion, and you have to couple it to it the position that you control, described as a constant times gamma dot, so this is a global velocity, plus some noise. So you are pulling at a constant velocity, but on top of this constant velocity, there is a noise that you have to put it like this to have the h Hertz exponent for the noise. And then you measure the stress, okay? So I will not go through the derivation of this because it's very long. But then you can find analytically a given exponent for the flow curve. And this exponent will be 1 over h plus 1 minus 1 over omega. Omega is 1 for Caspi and 2 for smooth. It's just how the potential behaves around the transition points, okay? If you have Caspi, you have the potential is a parabola, so the derivative is just linear. If you have a smooth, the potential in the transition point is a cubic formula, and then the omega is 2.
Can beta become negative?
Beta, sorry?
Can it become negative?
No, it does not. When it will become negative?
Let me see. Oh, it's one half. It's 1 or 1.
It's 1 or 2.
1 or 2. Okay,
And
okay,
this
that's
is 2
right.
thirds,
That's right. No.
so this is 3 halves
Never mind.
plus 1.
No, it's always
5
positive.
halves, yes, always, yes. Yes, yes. In fact, we should reobtain the same betas that we know already, 1.5 and 2. And you can do also with temperature. And temperature enters here, and then now you have not only beta, but 5, alpha, and beta, all in terms of h and omega. Okay? For the thermal rounding. And this is what we do with a one particle problem now. And we have the Caspi, and we see the thermal rounding for the flow curves and the collapse with the exponents that are supposed to be for the Caspi potential, and the same for the smooth potential with the exponents that are supposed to be with the smooth potential. So we are replace our completely extended system with a particle pulled in a disordered potential with the correct mechanical noise. And this h equal 2/3 represents 2D. If I were to do this for the 3D, I will need to use the noise that I would measure in 3D, okay, which is different.
This is 1D, right, your problem?
No, yeah. Well, yeah. The problem is now 1D.
Yeah.
But we are plugging here the value of h that we obtained from the simulations in 2D here.
Yeah.
What
right.
I'm saying is that in 2D, I obtained H067 in 3D will be, another thing will be a bit bigger. Yeah, in fact, okay. So, for this part, the take-home message is this. There is an equivalence between elastoplastic models and manifolds move non-quenched disorder. So we can represent yielding a la de pinning, let's say. This is the first thing we just said. There are two coexistent universality classes depending on the disorder potential being Caspi or smooth. The thermal rounding works without corrections in yielding in finite dimensions. There is a smooth variation of exponents when we interpolate with a generalized model between fully connected pinning and yielding. And then finally, our conclusion and our theoretical proposal for people actually to go and try to do more formal things on this is that the yielding in finite dimensions can be described as an effective mean field after you have characterized the noise, okay? Okay, so, fine. It's half an hour, no? Good. So, I want to go, if there are questions on this, maybe take them now.
Yeah, I want to ask something.
It's a bit conceptual. You know? The next thing will be more funny, I think.
Well, actually, I'm this problem that when we should take the particle.
Yes,
you know,
it's called Pram-Tomlinson.
It's very, I mean, it's very interesting because you can think about that in a very simple way.
Yeah.
But now it's puzzling why it works so well, you know, when you think about an elastic medium. That's no,
yeah.
it's.
I mean, I'm not saying it's not surprising, but I mean, after some time, I've learned to accept it and actually to push for it. I mean, I was skeptical about it because, I mean, yes, you have this 2D disorder system, amorphous solid whatsoever, but it seems that in statistical physics, long-range interactions are super powerful. They will erase whatever are on their way. I mean, and basically, I mean, as here, they end up putting all this information of the extended model and the rules, etc., in a single number, which is this noise. Yeah, that depends on dimension and depends. Well, another interesting thing is that it does not depend on the type of disorder because of potential, because the type of potential comes here separated from the edge. It's really very universal.
But if you have a random noise.
Yes, H 1/2.
Yeah, so then you would not recover your what you mean.
No, you don't recover the flow curves that we can measure with the elastoplastic model or the Hamiltonian model in 2D. So you get something else.
Yeah, okay.
You need to tune this. I mean, it's not that we have put it H in order to take back the flow curves that we know, but we have measured H. Okay, I mean, you have to accept things here. I mean, it's broadly distributed, etc. But okay, it has a clear mean value, is that. If you use this one, you obtain 1.5 and 2. So it's quite powerful. Yeah. We need to do this also in 3D to give further reasons, people. But okay, there are other things to do as well.
It's interesting.
Okay, so now first, I don't know how much I will be able to tell you about the problem that is coming, but let me first test your intuition a bit. Since you have heard about the pinning for some time now. So typically we have this, no? For the flow curve here goes linear whatsoever. As I said, mean this is a highly non-universal quantity. Depends on many things. In particular, plus, etc. Particular will depend on the strength of the elasticity or in the strength of the elasticity compared to the strength of the disorder. But okay, I mean, if for a given C1, let's say, for a given elasticity, I have this critical force, if I decrease the elasticity, it's like the configuration, if I decrease the elasticity, the configuration will be able to accommodate better in the landscape, okay? It goes deeper in the disorder when the elasticity, when the line can elongate more. So if I decrease the elasticity, we'll have a different FC, yes. Let's call this K, otherwise it's C and C. K2. And here K2 is smaller than K1, okay? Okay, I have the same equation of motion, two different parameters here. So now I have to ask the questions. What happens if I stand at a force here? Will I measure velocity, a finite velocity for one K and the other K? Yes, I mean, you see it in the plot, no? If I have a big force, bigger than these two, both lines, the one with K1 and K2 will move, okay? If I stand here, this one is already pinned. So the problem with K equal 2 will show a 0 velocity, and this one will move. If I put a force here, both are pinned, okay, in the long time. So now, what happens if I put a force here, and I switch equations between the one with K1 and the one with K2? What do you think will happen? Any guesses? So I fix a force, and now I switch between K1 and K2. So I will put here, I don't know, whatever, a sign of something changing K. What do you think will happen? It will move or not? No guesses?
You mean you put a
Now you
force
fix a
which-
force that is smaller than the two critical forces.
So your system is pinned completely?
Your system is pinned, but now you say, okay, I will vary the elastic constant. Instead of having a fixed value of the elastic constant, you vary. But I will vary between the one that corresponds to this critical force and the one that corresponds to that
But you
critical
vary
force.
in the system, you're
In the
creating
system,
a,
in the
a
system.
homogeneity now.
No, in the system now, as I said, I put some function of time here. I do it very slowly, but I vary K. Yeah, in fact, this is what we think. Yeah, but the response is that it does not, it moves. And it's a bit surprising, and this is what I will mention now, okay? I mean, you stay at a force that is smaller than the two critical forces, vary between the two cases, and the thing moves. And so this is the basis for this so-called thermal creep by cyclic perturbations. And it's related with geophysics, as you will see.
Because your critical
I'll
force
show you
depends
why.
on several parameters, not only on K, right?
Yeah, no, but all the rest of the parameters are fixed. Critical force is not changing. They are still these two. But you step below both, and now it's a different problem. This is what it is. And so it will be a subcritical movement.
By doing that, you change all the landscape
In fact,
in the system.
So, yeah, well,
So you can trigger things in different places because
you are
change
changing
the local
in
landscape
different,
in different places.
regions. So this variation of K will allow some regions to advance, and then you change K again to track the others that has not advanced. And since the force is still finite, I mean, you have a tilt on the potential, it will be like a ratcheting effect.
So it's similar to the phenomenon that I described, that if you heat and cool,
Yeah, I mean, it's
so
there.
you change the temperature,
Yeah, I mean,
although you are, yeah.
It's the next slide or the other, man.
Thank you.
Okay. In fact, yeah, after your talk, I decided to actually talk about this, really, because the slides were not ready and they're still not, but okay. So, our Earth is moving all the time. And so the hill slopes, in fact, move, and then you can see in some forests these trees bended because they try again to be vertical because the floor is going down. And actually, there have been a lot of activity recently on what is called the soft earth geophysics. It's a new community that is created and is bringing geophysicists and geologists and physicists together, and also is also led by two very active persons, Karen Daniels and Douglas Jerolmak, well, many others, but I mean, they wrote the first review on this. And I mean, there is a very, very nice message from this community I want to share with you, and it's what also attracted me to this. They say, I mean, we know a lot about what happens in distant galaxies and high energy physics and many other things where we studied. I mean, it's good because it's knowledge, it's important, but there is beneath of our feet, there are a lot of physics that we don't understand at all. Okay, so really there are catastrophes, etc. Now with the climate change, they are more frequent, and really there are many things that we don't know about the Earth. So this field, I think, is promising, and people are trying to, as I said, to join efforts from different fields in this interdisciplinary thing. And in order, I mean, try to contribute to this was also a very good motivation. So we'll talk about this creeping soil, which is in this kind of diagram at very low dimensionless shear rate, so very viscous, and very high packing fraction. But then here, then you have landslide, debris flow, rivers, etc. in this map, or in different scales. So one thing that people know from for the creeping slopes is that they are moving, as I said. And for example, here, if you put these tracer pegs originally vertical in the field, and I given one of these hills, well, this one was in Poland. This was originally vertical. You come 17 years later, and it's twisted like that. So all the thing moved there. And actually, again, this is quite universal. The shape of the displacement, it doesn't matter where you measure it on Earth or even in the lab. So this is a study done by Douglas and collaborators. So this is one indication that things are moving over very long periods of time. And you can also do it in your kitchen as well. Well, this is Eduardo's kitchen, and this is me. So we pour it in a container with an acrylic or a glass and a wood sand of two different colors, and then we put it there in an angle that is still below the critical one, so this is not just flowing away. And while it's in this subcritical angle, we press it many times, the glass towards the wood like this, no? Just to create some mechanical, and then you see this. Of course, there is a flowing layer on the top that will, but progressively, as a function of depth, you see that is like a kind of exponential form. No? It is as a function of depth. Deeper, okay, there is no movement, and then close to the surface more. Okay, so it's a very generic phenomenon. It's very nice to see. So the Douglas and collaborators, they have gone and done this other exponent and the experiment where they have the heap of sand, and they observed with the diffusing wave spectroscopy because they want to measure very little tiny movements, but they have all this under control. And after 11 days that they have poured the sand there in a subcritical angle, they come and still see movement. So this thing is still moving. Nothing. So this under no vibration table, etc. And it's just in the lab, sitting there, and it's still moving. They do perturb the system also to see how is the reaction with the heat pulse, with tapping, etc., etc. But I mean, the important are the conclusions, no? The creep occurred for all experiments, and it persisted over all time scales that they have observed. they say proving a seemingly static sampile, what we observe is that a ceaseless creeping motion, okay? Even in the near absence of mechanical disturbance. I mean, they cannot guarantee that, I don't know, bus passing nearby will do things to the air of the room whatsoever, but you do nothing and still there is creep. And they say, of course, our system is intentionally prepared close to the critical state. It's subcritical angle, but not flat, because if you put flat, then you cannot observe anything, okay? They have even a second paper where they see plastic avalanches and Eshelbys and etc. Try to also come closer to the amorphous solid community. But the thing again is that while there is a flowing layer where things go fast, but the bulk there is always creep, and there is aging in this creep, and then the level of creep that you obtain depends on where. How do you prepare your sample? There is one way of preparing it, strongly annealed, poorly annealed. It doesn't matter much. What I want to point out is that the creep persists in the absence of flowing layer. Even when they are not pouring any more sun, everything is steady, etc. You go day by day, after long periods of time, and still measure creep. So which are the creep mechanisms affecting this? Quiescent heaps in the lab or soil in the real earth dynamics? Well, certainly not thermally activated creep, as we have seen in the pinning, where temperature can make you jump barriers, because these are grains, sand, clays, whatsoever, organic matter, but it's macroscopic. Temperature cannot produce thermal activations. Can be mechanical induced creep, like wind, water, animals, whatever, earthquakes, and this happens, and of course this produces creep. But there is probably a more systematic deformation that can also produce creep, like variations of environmental parameters like day, night, winter, summer, temperature, humidity variations along the year. And this is the hypothesis, and in fact, well, Luis has shown already this, and his paper is here. Even though when the temperature cannot affect the granular system in the sense of producing rearrangements, it affects the contacts. No, it acts at the level of the friction. So if you have a cycle of temperature, the friction changes in the cycles, and eventually things start to slip. It was proposed already many years ago. This is 1856 by Mosley, trying to explain why the glaciers go down. And yeah, I mean, the idea is to think on a slab of material on an inclined plane in subcritical angle that undergoes thermal dilation and contraction, and in this way it can walk. Think on a compass. This is a very pictorial problem. You have a compass with a given spring there that is rigid, and you put it inclined, it will stay there, okay? If the angle is not big enough for it to actually slice, so there is some friction there. Now, let's close the spring that is in compass. Of course, the particle in the top is the one that will go down. I mean, it's unclear that you will close the spring and it will try to climb, no? It will go down. Now when you release again the spring, again, the one that will move is the one that is down. And after the cycle, you have advanced at delta x. This is when they show it like this, it's more or less intuitive. Tell me.
You say then the red part would act as a spring in your...
Yeah, it's a spring.
Okay.
You have it there, you make it harder.
Yeah.
You produce this, you lose it again, you make it softer, and then is this guy the one who moves. Yeah. And actually, I mean, you can see it with two particles and a spring and an incline, it's the same. The critical angle will be here, and where this acts as a, if K is fixed, this acts as a particle with friction, as we have seen in the first lecture. from the book of Barabasi, and we have this depending law. But I mean, if you do these cycles of K large and K small, K large, K small, you make the thing work, okay? And it will advance below the critical force. Now we will see what this alpha 0. So our approach will be with model of depending and yielding. I don't have too much time, but I will show what we found. And but more or less the idea is already given to you. No? Here we have this subcritical creep. Pictorially, this is what we observe. What as I've drawn in the blackboards for depending, we will see movement per cycle, a given finite delta x per cycle, below the critical forces when we alternate between KL and KS. And the same will happen for yielding. Well, this is a propagator we use, and we use this kind of disorder potential, but it can be any, okay? The depending is 2D here, but nearest neighbor interactions. And this is long range HLB as always. I mean, just to know that this is very generic. So these are the flow curves at a fixed value of K for the pinning. Different values of K. As you see, as you increase K, the critical point is there. So here I've shown you. It started from here and then decreased the elasticity and go to the right, okay? So these are the flow curves, or yes, the flow curves for, sorry, it's not the pinning. This is the yielding case, but they are analogous. This is a yielding case, and then if you subtract the sigma c for each of these curves, which is different, depends on K, you can have the exponent that is the same for all of them, is the universal 3/2. Now, you do this for the case where the stress is below the critical stress, and I'm taking here KL, the big K, as 3, which is the largest here. Critical force is like there. And now I'm switching between KL and different values of KS. And you see that the system works in all this range, okay? For a given amplitude KL, KS, we have a range where we can measure a finite delta gamma after each cycle. All this is steady state, very slowly deformed, okay? Not depending on frequencies whatsoever. And you see that the deformation that you obtain with this thermal creep thing is maximal close to the critical force, and then it goes down and eventually goes to 0. Okay? And even more interesting, if you subtract the sigma 0 for each of these values of KS, you obtain this, seem to reobtain the same criticality as before because it's the same beta, but now in sigma 0, okay? It's like the criticality shifts from sigma C to sigma 0. This is showing you the critical stress as a function of K, is the blue curve. And here are curves for sigma 0, this value of the stress, below which you cannot even see movement with this oscillation of K. So there is a limit for this creep. But just to say that the range where you can observe it is bigger as KL is bigger, and it's maximal when KS is 0. Really, when we are putting a spring, then completely erasing it or releasing it to a spring that is very, very, very soft, and then we put the hard spring again, very, very soft hard again. Okay. And we can also see the width of the manifold. Okay, as I showed you in the first lecture, the width of the manifold is also diverging at sigma c when you have the typical transition. In yielding, we can only obtain it coming from below, but it has an exponent, and when we do the oscillatory K case, it diverges with the same exponent at sigma 0. So more evidence for this criticality moving to sigma c to sigma 0. And here is exactly the same thing for the pinning, okay? With the pinning exponents, but exactly the same thing as before. now we have the width diverging both from the right and the left. And in the pinning, we know the exponents. And in fact, the exponents we measure for the width diverging at the critical force are the ones that you expect from other works in the pinning, okay? And it's the same at sigma 0 when you do this oscillatory shear protocol due to variations in the elastic constant K. And so finally, the schematics to understand this is what I already replied to Luis, or he already thought, is that, I mean, you have your system, each block of your system is either trapped on a potential or in the path between one potential and the other. The thing is that here, the average position will tune to an equilibration of forces between the springs and the global force that you are pointing there. Okay, and this is when you are in with the hard constant of the spring. When you release it, or when you decrease it, some of the blocks will be able to advance because there is a tilt given by the force. Will be able to advance, and eventually they find a potential well forward, so they get trapped there. And when you, again, make the spring harder, those that got trapped in a forward position will track the ones that are more delayed and eventually pull some of them out of their wells and bring them forward. And this is the mechanism. There is a little backward motion as well when you change the case, but in total, it's more forward motion than backward motion, at least while the force is bigger than F0, okay? So you can then go and see all the details of the dynamics. And if you do, instead of quasi-static, you do more rapid changes, this also will affect, okay? So the summary is that when the external driving force is below the critical threshold, there is a regime in which the system exhibits this synchronized evolution with the periodic variation of the elastic rigidity, okay? So it's a new, at least in the pinning and gilding, it's a new mechanism for creep, okay? The deformation per cycle, this delta X or delta gamma, decreases as F if reduced and vanishes at a well-defined threshold F0. That depends on the amplitude of the case, but it's well-defined for each case. And it's very much like the insurance limit of fatigue, you know? I mean, for fatigue, I mean, when you want to break a wire, you do this many times until there is something that travels and you break it. So it's like, if you have a fracture there, you can also do this, for the fracture to advance, okay? But there is a limit. I mean, if you do very little force, the fracture will not advance, okay? You will be able to move it after a given threshold. And this is called the endurance limit, okay? And this is similar to that. I mean, we do oscillations, but you need to do them with a given force applied, otherwise it does not move. It seems that the criticality at this endurance point, or F0 or sigma 0, is analogous to the one at FC. So you shift the criticality. While creep is larger when you are closer to sigma C, as also the geophysicists expected when they prepare their heap of granular system close to the critical angle to see more movement, okay? And these experiments support indirectly our hypothesis is that periodic environmental changes, temperature, humidity, you name it, I mean, you can start thinking of many things. Temperature, as Luis was referring to, affecting the friction, but you can also think on periods of humidity that make clays more sticker and less sticker in between them, so changing the interactions of the particles, of the granular particles at the granular level. They can induce these periodic oscillations that even with a subcritical system will produce a finite movement of the system at the end. So periodic oscillation in the internal parameters of the system. And okay, there are some references. And I want to finish, okay, by thanking the organizers again, thanking all of you for the attention, thanking my collaborators. I want to invite you to come to Bariloche, to those that you can. I mean, I will be there. Just drop me an email if you are thinking of, that you are interested in any of these things. There is also Eduardo and Alejandro to discuss there, and we can try to find ways for you to come. It's a very nice place for those who have never been there. And also, I mean, you are a very young people. You don't need to worry yet about the editorial asks, but for you to pass the word eventually. We have this journal called Papers in Physics, that's also Luis advertised it in his talk. It's run by scientists and it's for scientists, and it's completely non-profit. And in fact, we have it on our shoulders. Carolina and me are managing editor of the journal at this moment. And Luis has been one of the founders of the journal. And we need new energy, okay? Because it's a lot of work, and we are looking for people to take over or to help. So maybe, you know, it's an effort based on Latin America for the managing part, but we have an international board of advisors and section editors, of course. Well, you can also, it's worth going and taking a look to it and thinking on submitting your papers there as well. This is a way of helping, okay? With this, I think again, finished. Thank you very much.